All right. Welcome again, everyone, to today's webinar on UL 3741. I wanted to go through some housekeeping items before we begin. You can join the audio either via your computer or your phone. And the webinar is being recorded and will be shared along with some resources via email within the next week or so. Please note that attendee microphones are muted, but you can use the chat function or the questions function throughout the webinar to leave questions, and we'll address them at the end. Okay, so with those out of the way, let me introduce myself and the speakers for today. Jacob, next slide, please. Okay, so I'm Varsha, a Senior Product Marketing Manager at SolarEdge, and joining me today is Jason Bobrook, who is our Director of Code Compliance. He's our expert on UL 3741 code. And we also have Kleber Fakini, who is our Director of Technical Marketing, C&I, and Jacob Favor, who is our Field Applications Engineer on C&I as well. Next slide, Jacob. So we're in for an engaging and informative session here today. And in terms of the agenda, Kleber will be kicking things off by emphasizing the importance of safety and the challenges in maintaining code compliance. Following that, Jason will provide a comprehensive understanding of the UL 3741 standard and introduce SolarEdge's UL 3741 solution. He'll also touch on the constraints of non-DC optimized solutions. And finally, Jacob will be delving into the compelling cost advantages of DC optimization and its direct correlation to balance of system savings and OpEx reductions. He'll also share insights on how this solution can significantly boost energy revenue. And all of these calculations that he will be presenting today are backed by a study that was validated by a third-party engineering firm called Pure Power Engineering. And after going through these slides, we'll be opening up the floor to your questions during our Q&A session. So again, feel free to leave questions throughout the webinar, and we'll start addressing them at the end. So without further ado, let's dive right into our first topic with Kleber. Kleber, handing it off to you.
All right. Thank you, Varsha. Good morning, good afternoon. Greetings, everyone. Thank you so much, for joining us. Appreciate, that your audience. And we are once more, right, trying to bring to the market, right, trying to industry, talking about this topic, that's very, I would say, timely, and also a topic, right, that we want to make sure that is top of mind of everyone, right? So my part is going to be a few minutes, 5 minutes tops, then I'll pass to Jason, into Jacob, that is going to go into more details, as Varsha mentioned. So I'd like to start, with a high-level safety message and then introduction to the webinar. Our solution, as you can see here, with DC optimizers, bring a holistic solution in terms of safety. Due to the DC optimizers that are integral to our solution, the array voltage level, right, is brought to touch-safe voltage levels within seconds upon a fault or due to maintenance. The inverter and optimizers work together to provide early detection of potential arc faults, and all monitoring happens down to the PV module level because of the DC optimizers. We have lived by these principles and will continue to educate the industry on the importance of a safe PV system. So now to the main topic, right, of discussion for this webinar. The introduction of UL 3741 standard for PV hazard control in 2020 was seen as an important milestone in the solar industry continuing drive to improve solar system safety. Building on rapid shutdown best practices first introduced in the 2014 code, or the NEC 2014, it was created to equip the solar industry with more options to accomplish compliance to rapid shutdown in PV arrays, with the primary objective to protect firefighters when responding to issues at solar installations. In this respect, 3741 has achieved some success, or good success, I should say. However, concerns are rising regarding the safety of some of the PV hazard control solutions that have entered the market since the regulations introduction. Okay, UL 3741, the standard, opened the door to allow solutions that use few, if any, MLPE devices to be compliant, to be code compliant. And in these solutions, AC contactors conductors are de-energized using traditional string inverters. However, the DC array itself is kept at a high voltage levels, 1000 volts, even after a rapid shutdown is initiated. To mitigate this increased risk, the standard states that solar arrays need to be made safe and not allow any exposure to dangerous voltages during firefight interaction. This means that every wire, module, or energized component in the array that can be accessed during firefighter operations must be protected from damage using robust wire protection measures such as sturdy wire guards or conduits. And it is at this point, that some of these alternative solutions start to lose traction. And this is not due to any flaws in the standard itself, but rather it is because of the way it is being interpreted by some manufacturers and certification agencies. Jacob, can you advance to the next one? The biggest concern in systems without MLPs, or the one that I just described using string inverters or with little MLPs, is that exposed accessible live wires with voltage levels up to 1000 volts are held in place by nothing more than plastic cable ties or plastic raceways. From day one, those exposed live wires may pose a significant risk to firefighters, and that risk will only increase as normal wear and tear, including sun exposure and snow and wind, could potentially cause the plastic ties and raceways to deteriorate. Once this happens, more sections of conductors may become exposed, accelerating the shock hazard risk to firefighters. Furthermore, the likelihood of arc faults and ground faults developing into fires is increased as the array will be maintained at 1000 volts DC, even during array or inverter faults. And these solutions put firefighters and O&M personnel at risk, and asset managers beyond firefighters, should also be concerned that with some non-MLP solutions, field crews will have to work around 1000 volts DC. The hazards of an accidental short or broken module can be exacerbated by the 1000 volt voltage level present in the array. So with that, I'll pass that on to Jason.
Hi, folks. Thanks for coming today. I'm going to do a quick review. I'll try to keep it short because we want to have lots of good questions at the end. So feel free to keep those questions coming in the Varsha, I guess in the questions box is where folks would enter questions versus the chat.
That is correct. Yeah.
We'll get right into it. So we'll talk about why it's necessary. Basically what it is, as deep as we can go in 10 minutes. And how does it work? So just discuss those basic principles. So we'll go ahead and roll to the next slide. Thanks, Jacob. So why was it conceived? So originally, NEC 2017 had an allowance for a listed array. That's about all it said. It didn't say what standard to use. So a standard had to be developed, and that standard was 3741. And that gives the methods necessary to evaluate an entire array assembly, to look at methods that are used to reduce electrocution hazards. So firefighters typically want to turn things off before they, go into a building or do some firefighting operations on a wall or within a dwelling. But as we all know, it's hard to turn off a PV array in the daytime, right? So the DC array, the string, remains energized if there's sunlight shining on the modules. So the 80 volt threshold, the history behind that was that was a simple number to draw from. It came from the arc fault detection equipment call out in NEC, and it's a conservative method. And so there was an allowance, people call it option 2, which was use some sort of rapid shutdown device within the array to keep, or voltage attenuation device to keep the voltage below 80 volts. And then there was a third option that was option 3, which is important, I think, to consider because this is kind of the philosophy or the background, if you will, of some of the PV hazard control approaches, was to put some separation between energized parts and grounded metal. And so that was for basically designed for building integrated photovoltaics, where you had no metallic exposed parts on the module, and then you were 8 feet away from some other grounded part on the rooftop. That background is important to understand how we kind of move forward with evaluating arrays. We'll go ahead and go to the next one. All right, so just a quick review. Hopefully everybody's already familiar with this. NEC 2020, NEC 2023, all give allowances for what to do inside the array. So you have 3 options. We just talked about those. Hazard control system, PV hazard control system is one option. The standard to evaluate that is UL 3741. The next option is voltage reduction in 30 seconds. The standard to evaluate that one is 1741, or no exposed wiring and 8 feet separation. That standard today would be 3741, but that option is actually no longer in NEC 2023. And the reason is because of the PV hazard control standard. So it seems redundant to keep that option. And so just a quick diagram on the right, so folks can visualize the array boundary. So these requirements that we're talking about are for inside the array boundary, right? There's 2 zones. You have the array boundary in this picture is represented by the pink colored box. So you have outside the array boundary, which rapid shutdown always applies outside the array boundary. You don't have any options. You have to reduce the voltage to less than 30 volts in less than 30 seconds. No other options there. Inside the array boundary is where you have the 3 options that we're going to talk about. All right, let's go to the next one. Thank you. Also, what is a PV hazard control system? That's a pretty difficult question to ask sometimes, because it can be a lot of different things. And so what I did was I just grabbed the scope out of 3741, and it says that the requirements in this standard provide a means for evaluation of components in a system that provide a reduced level of shock hazard from energized PV system equipment and circuits located within the array after the operation of hazard control initiation functions. So that would be, for example, rapid shutdown initiation. The standard's pretty specific that while the equipment, PV hazard control equipment, may reduce hazards for other folks, it's really intended to focus on firefighters and firefighter interactions. So that's the primary focus of the array, is for firefighter safety. All right, let's roll on to the next one. Thank you. So this gives a nice little electrical diagram of what the standard is trying to accomplish from an electrocution standpoint. So the basic premise of the standard, this is kind of high level. I encourage folks that haven't read it yet to go on the UL website. You can look at a free copy. You can actually read through the details. But the premise was to take a scientific approach rather than use the 80 volts that came from the arc fault requirement, and model those electric hazards. So Sandia and UL worked together to develop, to do some very great research and develop a firefighter body impedance model, and along with PPE resistance models as well for gloves, boots, the turnout gear, which is the pants, to look at the entire envelope of how a current might flow through the body. So that's like kind of the body impedance model that was developed. That information from that model was used to determine how to compute the hazards in the hazard array in the PV hazard control standard. So the PV hazard control standard doesn't say you have to do all this body modeling, but what it does is takes data from that research and says, okay, here's how you compute the current that might flow through the body. And so you can see in the diagram here that the little stick figure on the left is modeled as a bunch of resistors. It's kind of essentially how we look electrically. And then if you have a fault in one location, fault 1 kind of in the upper left there, and you have a ground path reference or a fault in a second location, that would be at the ground level, fault 2, then current could flow if there's voltage potential between those 2 points. Current will take the path of least resistance. And if that happens to be a person, then the current's going to go through the person. So the model assumes, different types of people, women, men, is somebody perspirating, what type of PPE are they wearing? And in fact, when you go through the analysis, you can look at the resistance of the gloves and the pants and things like that. You add all that up to get the current flow through the model. So the hazard arises, inherently the PV system is safe until it's damaged, right? We've all been working with PV systems, installing PV systems. So it's not like we're just laying open energized conductors out there for folks to grab, but it's when the firefighters are taking an approach to the array, or they're working on ventilating the roof, or just simply traversing across the roof, that they might come in contact with that array, and that's when the interaction could occur that might damage the array. So it could damage insulation on conductors, you could damage a PV module, junction box, etc. But all of those things that could become damaged could get damaged in a way where it exposes a person to those conductive parts, and so in those energized parts. And that's what the standard is trying to evaluate. So it's not trying to evaluate an array that's not damaged, it's more damage during a firefighter interaction. So you'll hear that term over and over again, firefighter interaction. So let's go ahead and go to the next one. All right, so I think I jumped too quick because we had animations, but what I wanted to say was that some of the means to protect against those interactions are electronic means or mechanical means. Thanks, Jacob. I'm back. I didn't realize we had animated bullets. So, so that's one means. You can turn the thing off. It's kind of what we do with module level power electronics, or you can provide a physical barrier or separation between those live parts. That would be a mechanical means of protection. And again, everything assumes that this is a firefighter that's using intact personal protective equipment. All that is on. So you're not looking at an interaction with, bare skin per se. You're looking at something, you're grabbing something with a glove perhaps, or a boot, or your clothing might be touching an energized part. All right, let's go to the next one. So again, there's not enough time to go through the complete safety analysis in this presentation, but just the purpose of this slide is just to show that it can be complex or it can be simple, and it depends on what the solution is. So for example, when we use a voltage control method, like rapid shutdown at the module level with module level electronics, the process is fairly simple because we're really depending on the rapid shutdown standard, right? We're saying this component de-energizes the hazardous parts, and therefore we don't need to go through an additional safety analysis or the likelihood of somebody coming in contact with that part because we've just de-energized it. So you kind of follow the flow chart in the middle, you do the safety analysis, you demonstrate is hazard control demonstrated, yes or no, great. If you're doing a mechanical solution, it's a little bit more complex because you have to demonstrate that you've maintained that separation from conductors or guarding or physical protection upon the damage that a firefighter might put on the component. So then you have to kind of go through a little more complicated analysis, which is that small flow chart on the left, where you look at the interactions, like falling on the array with a tool in hand, for example, the probability of that interaction, and then what's the hazard level as a result. All right, so let's move on. We're getting a little short on time here. Great, so we talked a lot about hazard levels and voltage levels. I made this slide to kind of help illustrate that. The table on the right, the white table without the coloring, comes directly from the PV hazard control standard 3741, which was actually borrowed from an IEC table, and it shows how to assign a hazard level to current that can flow through a person, and then what the result is. That's the description on the right. And then the colorful section on the left, I just associated voltage levels as an example with those various current levels, because we all kind of know what the voltage levels within the array are. When you start asking what's the current level when somebody grabs something, that's a little harder to conceptualize. So I'm just lining these up. And this example is pretty specific. So the example is the worst case example, which is a firefighter falling on the array with a tool and belt that pierces a module or cuts a wire and exposes string voltage. And then the current path is from the hand to the hip. It's a pretty short current path, right? You would go through your hand and maybe your hip is touching a rail or something like that. And so you're looking at that current path. And so that using voltages in that example, you can tie those to the current levels just using the resistive math that's in the standard. So you see right away that as keeping the voltage low, you can stay at a hazard level 1 or lower. And that's essentially what we do with module level power electronics. There's a sweet spot there at about 165 volts. It turns out that doing the math, you end up, that's about the maximum voltage that you can go to without any additional means of protection. Everything below that, you're above a hazard level 1, which is not allowed. So you have to add some additional means of protection. And just to put things to scale, when you get up to 1,000 volts, you're pretty much off the chart, right? The chart kind of stops at hazard level 3, so you could claim hazard level 3, but that really starts at 100 milliamps. You're up at around 460 milliamps during that firefighter interaction. So that's where the enhanced protection becomes very important, right? You don't want to be able to damage that conductor or that junction box or module or whatever to get to that voltage in the first place. So you use some sort of additional means of protection. All right, let's go ahead and roll the next one. All right, and so with that additional means of protection comes more responsibility. And so systems that, this comes right from the standard, right? Systems relying on mechanical protection or isolation will rely more heavily on design construction measures than those with inherently low operating voltage, for example. So really what this means is the responsibility to maintain that safety system is essentially transferred from the manufacturer to the installer, right? If you don't install those enhanced protective measures correctly in the field, then you don't have a compliant safety system. So there's kind of a shift, if you will, of, I don't know what to say, if it's a shift of responsibility or a shift of scope from requiring solely on a manufacturer's piece of equipment and its listing versus requiring on the assembly of a safety system with multiple components. And that really, the success of that really hinges on the quality of workmanship and the checking for human errors, right? We've all installed PV arrays and forgot to put a couple bolts in or a wind deflector or something. Where does that go? I got to go figure out how to put that thing together. There's just a lot more going on there and a lot more stuff to deal with. Not to say that it's impossible. It takes some more responsibility and some more thought. And you got to observe those components. All right, let's roll on to the last slides here. And SolarEdge's system here, we use voltage protection. So I just talked a lot about mechanical protection. The example of voltage protection is a little bit different. I'll talk about our example because this is what we make. So we just remove the hazardous energy by lowering the voltage, which takes away any dependency on a mechanical system. So there's no other enhanced means of protection that are needed. We consider the worst case probability in interactions, and the standard allows you to do that and kind of forego any testing. So you can say, hey, I'm just going to consider everything at worst case, so I don't have to go to this mechanical robustness test or wire cut test or whatever. We just assume the wire's cut, right? On the input of the optimizer, we say the interaction is with 125 volts DC. You can go compute the current through the body with PPE on, and it's a hazard level 1. It's below hazard level 1 slightly, and that's good. That means that you've achieved that safety system. So voltage control, if you go to a low enough voltage, makes life pretty easy. If you're at a higher voltage, you may have to do something else. So if you were above that kind of magic number that we talked about, 165, you'd need to do some additional means of protection, which could be some other supplemental guarding or separation or something. You could use a combination of electrical means and mechanical means if you want. So our system doesn't require any dependency on racking or raceways or inverter placement or anything like that. All of those things are kind of out of scope for our system. Our system is really just the optimizer and the inverter. So we control that by controlling the input rating of the optimizer. All right, great. So we'll move on to the next one. I think I've gone a couple minutes over, so I'll try to go even faster. This just gives a quick example of mechanical means versus electronic means. And I just put the voltages up there. Green means you're kind of below that hazard level 1. Red means you're above the hazard level 1s. So we're looking at 2 modules in series as an example here. In the electronic control system, you can see the optimizer in the middle between the 2 modules. Once rapid shutdown is applied, you don't need any other protective means. You're at hazard level 1. If there was no optimizer there and you had a string of 20 or so modules, then you would be at around 1,000 volts DC, and you would have to do something in addition to what you see on the screen here. So what you see on the screen here is kind of a typical system with wire management. Somebody's kind of gathered up the conductors and put them on the railing there to keep them off the ground. that wouldn't be good enough. You'd have to do something to protect that firefighter interaction. Obviously, somebody can access that during firefighter interactions. So if they were to, fall against it or accidentally, backswing or something with an axe, they could cut that conductor and it would be right next to a grounded rail. And so there's an opportunity for somebody to get referenced between ground and that energized part. So we'll go ahead and go to the last slide and close it up here. Great. So what I did was all the things I've been talking about, I kind of put in a quick table, pros and cons of the different systems. With voltage control on the left and a mechanical means on the right, obviously energy's turned off versus energy left on. We like to say the electrocution risk is removed versus the electrocution risk is hidden or tucked away or guarded. One other important thing to talk about that I didn't really get into too much was testing the system. So with rapid shutdown systems, the standard requires that there's a self-test. We actually do an automatic self-test every day. So every day that safety system is confirmed. With the mechanical systems, there's no self-test, unfortunately. So that has to be handled in another way. With installer error on module level power electronics, the system simply doesn't work. It will shut down. If there's an installer error on a mechanical assembly, the PV system could still work. Unless you're doing a thorough visual inspection, you may not know that that guard was missed or that wire management component was missed or that separation is too close between conductors, right? So there could be a shock hazard if there's an error. Compliance is maintained by the equipment. I talked about that already versus compliance maintained by the installer. No dependency on components with MLPE. You're highly dependent on components with the mechanical systems. So there's no ongoing inspections required with PV rapid shutdown. Devices, they either work or they don't work, and they're required to fail safe, right? So if a rapid shutdown device fails, the safety standard says, hey, it has to fail in off mode. It can't fail on and just remain on, right? There is no inspection for that or test for that with a mechanical system. I haven't thought of one yet. I guess you could go up and yank on the wires and pull on the guards and make sure everything is in place and robust. But I think that's something that's still evolving. But at the moment, we have to assume that requires a frequent ongoing inspection just to maintain that compliance and that safety system. So there's a lot of history with electronic means. There's really not a lot of history yet with these mechanical means. I think we've got a couple of years now, but there's a lot of lessons learned that are coming out of this. And then the last but not least, mechanical systems typically don't consider other O&M personnel. So somebody who's not a fully equipped PPE firefighter may not be protected, right? Because when you calculate that current path, you're depending on the gear that the firefighter is wearing. Operations people may not have that gear, and they're not trained in that way to interact with the array. So there's really no protection from them. Again, the standard wasn't designed to protect O&M folks, but it doesn't offer anything for them. So voltage control does. So that's why we have what we call Safety C. You can turn the thing off, you can de-energize the array, you can go safely work on the modules without worrying about being exposed to higher voltages. So thank you. I'll turn it over to Jacob, who's going to talk about some of the advantages and disadvantages in the financial analysis.
Great. Yeah, thank you, Jason. So hi, everyone. Thanks for being here. I'm going to shift gears a little bit, move away from the safety compliance discussion, talk a little bit more about dollars and cents. And please keep on throwing your questions in. The ones that we don't cover in our presentation, we'll get to pretty soon here. So some people might expect that removing MLPEs from the rooftop is a big cost-saving opportunity. And what we wanted to do is take a closer look at those claims. And what we have done is taken 5 typical rooftop C&I PV systems of various size and basically done a head-to-head design for 2 different options under UL 3741. So one using a SolarEdge DC optimized solution, and the other one using a non-DC optimized racking solution. And as Varsha mentioned, these system designs have undergone independent review and verification by Pure Power Engineering. So what we've determined over 5 case studies is that savings on electrical balance of system are pretty consistent across the spectrum. And there is up to an even over 50% savings on balance of system when using a DC optimized solution. So the big question is why? And at the root of these costs is typically design flexibility. So with a traditional string inverter, you'll need to install within 1 foot of the array to remain 3741 compliant. This means inverters can't be installed at a centralized location or at ground level, which is leading to increased AC balance of system costs. AC cabling runs are more expensive. They need to be oversized to keep resistance losses low, and they're just generally going to be much longer. So on the other hand, on the right side here, you can see a SolarEdge system would allow for installation of inverters at a centralized location or at the ground level, and you can use aluminum cables on the DC side to further cost reductions. So the inverter placement is very important when we get into this cost analysis, as well as the use of PV rapid shutdown equipment. So fire code typically requires that there are walkways every 150 feet within an array. And this is requiring the use of PV rapid shutdown equipment, listed PV rapid shutdown equipment, when a non-DC optimized solution to UL 3741 is used. And that's to maintain the below 80 volt threshold between sub-array on the rooftop. So you can see in this image how inverters and PVRSC devices are distributed throughout the rooftop to maintain compliance with 3741 and the NEC. As compared to a DC optimized design, no PVRSC is required because hazard reduction is occurring at the module level. As well, inverters can be located centrally near to the AC switchgear or grid interconnection. So when we look at those two design variants head to head, what you can see is that AC cabling from your inverter to your combiner and from your combiner to the interconnect is going to be much more expensive for a non-DC optimized solution. And when we looked at an average across all the case studies, we estimate that the AC cabling, the conduit, grounding, and the install labor account for an increased cost of 4 to 5 cents per watt DC. Another reason for BOS cost increases is the specialized racking. So as Jason mentioned, particular accessories will be needed for protecting from hazards if a non-DC optimized solution is used. So SolarEdge's DC optimized solution doesn't require any special racking or special accessories to be compliant with 3741. These types of accessories are needed for limiting exposure to high voltage between rows and columns of the array, as well as maintaining gap distances between cables and any metal parts of the PV frame or racking structure. So there's a couple images here that show some examples available on the market for accessories to limit exposure to the hazard source. And when we look at an average across all of the case studies, we estimate that the increase of cost for the labor and the accessories themselves accounts for about 1 to 1.5 cents per watt DC increase. And the third reason that we see cost increases for non-DC optimized solution is the use of MLPEs or PV rapid shutdown equipment to maintain NEC compliance between subarrays. So it's possible in some smaller systems to avoid the use of these entirely, but it is quite rare to have a C&I rooftop without at least some breaks in the array for the reason of fire code walkways or rooftop obstructions that need to have access. So one of the options for non-DC optimized solutions is to use listed PV rapid shutdown equipment whenever strings cross the gap between two subarrays. So this image shows here that you need 1 to 2 of these devices roughly per subarray. That's for this system. Another option available is to use MLPEs on portions of the rooftop. So for any individual module that is connected to an inverter in a different array, you can see that that module will need to have MLPE, like an RSD device, connected at the module level for anytime if the inverter is across the gap between two different subarrays. So again, we looked at across 5 case studies using a couple of those different strategies. The estimated increase of cost for adding NLPEs or PVRSC is about half a cent to 1 cent per watt DC. So back to the elephant in the room, so to speak. Balance of system savings are great, but the big question is, can they make up for the cost of NLPEs? So we took a market research average of 7 cents per watt cost for inverter equipment. That's from the NREL, National Research and Energy Laboratory, I think. We put together a final estimate of all the capital expenses, including price of equipment, inverters, and NLPEs where used, balance of systems, and the labor costs. So in fact, across our case studies, non-DC optimized solutions are more expensive in 3 of the 5 systems that we analyzed. And of course, we expect to see some variance. This depends on many things, including shapes of the rooftop, what strategies are being used for 3741 compliance, what accessories are being used. But it may very well be the case that on an upfront cost CapEx basis, DC optimized solutions are more cost effective. So moving on from the upfront basis, we wanted to take a look as well at the OpEx cost for a system throughout its life. If DC optimization is not used, we've identified additional tasks and costs that will be introduced for a project. And we identified these by discussing with a variety of O&M providers, and the following list of tasks were identified. So IV curve tracing is something that needs to be done to debug issues at the array level. Infrared scanning, thermal imagery or visual inspection is required if there are issues with PV connectors. So both of these practices are typically used only when production or on-site issues occur. As such, we've modeled the likelihood for these costs occurring using a bathtub model, bathtub curve, which means it's going to happen more often in the early life of the system during commissioning and end of life of the system. In contrast, with DC optimization solutions, you're getting continuous and granular module level data, which enables real-time monitoring of any issue at the DC array. So that includes temperature sensors within optimizer connectors that are going to cease inverter operation, lowering DC voltage in case of any connector issues. Annual drone inspections and reports as well is a pretty common practice done yearly, which is not necessary if you have real-time monitoring from your array. And the annual inspection for array safety compliance. So to make sure that the system using mechanical means is still protective, providing benefit to firefighters, it would need a in-person inspection of the mechanical components, make sure that they haven't overly aged and are still robust to provide that protection that would have been inspected at first install. As opposed to a DC optimized solution that performs a daily self-test of the rapid shutdown feature on each optimizer. And finally, solutions without DC optimization and module level monitoring are going to require truck rolls for issues in the array to be investigated. And so when we model those costs over a 20-year lifespan, you can expect an additional cost of up to $60,000 in net present value. That's per megawatt DC. And so when we include an estimate of those additional OpEx costs for the full lifespan of a non-DC optimized system, that's 20-year lifespan, the overall system cost is going to lean even more heavily in favor of utilizing DC optimized solutions. And finally, we want to look at the revenue side of things and do a comparison of energy production. So all PV panels experience mismatch, and this mismatch can cause power losses and drag down your system's overall performance. Traditional PV systems with string inverters, when one module produces less energy due to mismatch, if it's shading, soiling, production, manufacturing differences, there's any sort of number of reasons, the entire string's production is going to be lowered accordingly. When you use module level optimization, the power losses are mitigated, and that's going to result in overall higher power generation across the system. And so we took these same 5 case studies and we ran an energy analysis by a PV syst for year 1 and year 20. And what we found is the gains with DC optimization can be up to 5% over the lifetime of the project. And we can estimate the corresponding revenue increase for that if we use a known utility rate, a fixed inflation rate, and an annual escalator over 20 years. So on average, across these 5 case studies, the net present value revenue increase is roughly 7 cents per watt per project. And again, the methods used for this production simulation have been independently reviewed and validated by Pure Power Engineering. So finally, what we do is we're going to include the difference in expected energy revenue over a full system lifespan as an offset to system costs. And you can see that the value of a DC optimized solution, not just the upfront costs, is clearly much preferable to that of using non-DC optimized solutions. So we'll quickly just summarize the main points here. Obviously, number 1 is safety. And with a DC optimized solution, you have an enhanced safety feature by using automated and engineered protections that are removing the hazards, as opposed to mechanical components that are meant to protect and hide hazards. On the BOS side of things, up to 50% savings on electrical BOS is possible by reducing the number of DC strings, decreasing the length of AC cable runs, and avoiding the use of additional accessories for hazard control. Energy production, increased revenues over the system lifespan. The O&M costs will be decreased by leveraging web-based real-time monitoring at the optimizer level. And finally, the design flexibility that is afforded to DC optimized solutions allow you to install inverters at a central location or at the ground level, if that's your preference. The array itself can be broken into subarrays, maximizing the space on the rooftop, increasing your capacity without the need to add additional PV rapid shutdown equipment. So with that, I'll pass it back to Varsha to talk more about some of our resources.
Thanks, Jacob. That was a very insightful presentation. Thank you all. So before we jump into the Q&A section, I just wanted to direct your attention to some of the other resources that are available to enhance your understanding on the topics that we've discussed today. So we have articles on magazines like PV Magazine and Solar Power World that you could explore for a more comprehensive perspective on the comparison between DC optimized and non-DC optimized solutions. And we also recently released this white paper where the analysis that Jacob just went through in his previous session is in further more detail. So there's a detailed breakdown of the 5 case studies, and it also delves into the assumptions and the methods used for these estimates. And we highly recommend going through this white paper for anybody who's seeking a deeper understanding on this subject. And lastly, just a reminder that we will provide you with all these resources and a copy of the recording through an email next week. So with that, let me open up the questions here. We have quite a few coming in. Okay, let's dive into some of them. Okay, so there is a question here. How long are the safety critical wire management parts that would be required for code compliance, like plastic zip ties, expected to last? Jason, can you take that one up?
Sure, that's a good one. I actually asked one of the manufacturers this at a trade show, and they said 2 to 3 years, and they were talking about the UV enhanced type wire tie. I think it's polyamide 6 something 66 or something like that. But even with that enhanced chemistry, depending on the weather and the solar exposure, et cetera, they're only seeing 2 to 3 years out of that part. So I think that actually kind of plays into one of the points we made, is that you'll have to do some sort of inspections if you're using that component to comply with PV hazard control. If it's not a critical component for PV hazard control, then it's more of an aesthetic thing, right? But there are systems out there that use those as critical components.
Okay, makes sense. Thanks, Jason. There's another question. Since mechanical systems don't have an electronic automatic self-check to maintain the UL listing, how often should they be tested or inspected to ensure that they still comply? I think, Clever, this is a good one for you. You can answer.
Sure. Yeah, and this is also, I mean, another point, right? I mean, that we definitely would like to understand. I mean, that we want to talk about. I mean, there is no necessary, like I would say, every so often, right? I mean, to have that to have the inspection. But that's one thing that we wanted to discuss, right? I mean, there is no requirement in the standard, but what happens, right? I mean, like 2 3 years down the road, like, I mean, we discussed, I mean, if the cable ties, the wire, the raceways, start to deteriorate, what will happen, right? I mean, so as long as that kind of become expose firefighters, expose O&M personnel, or anyone that's going to go up in the roof, to expose to wires that, guess what, right? I mean, if you don't have an MLP, it's going to be energized at 1,000 volts.
I'll touch on that one too. I think the two key principles of what's called enhanced protection by the standard are isolation and separation. And so the component has to maintain that insulation is another good word, right? That the component has to maintain that value for either for the life of the system, or it has to be replaced on an O&M schedule. And so I think the industry is still on a learning curve here, right? Some of these things that haven't been depended on previously for this type of safety system. And so I think it remains to be seen how long will they maintain that level of safety. And so it gets, the impact is one thing, falling on something with a sharp tool, stepping on it, that's one of the firefighter interactions as well. So I think we can you could ask those component manufacturers, you can talk to the solution providers, but I've asked around and I got one answer already. That was it for the wire management.
Got it. Yeah, thanks, Jason and Clever. Let's see. Yeah, keep them coming, you guys. The questions are all good. There is a question here. Firefighters are used to expecting 80 volts within the array, typically. Now with 1,000 volts allowed, how do we know the difference? Are there any signs, Jason?
Are there any signs? Okay.
Mm-hmm.
Well, that's a good one. You don't really know the difference, right? When you're inside the array boundary, right? There's a sign required for rapid shutdown. Typically, it's at the ground level near the initiator that says, rapid shutdown system. But once you're on the rooftop, there's no required signage that says this system's using voltage control, this system's not using voltage control. So I think you have to proceed with caution. And of course, the firefighters aren't trained to intentionally go and destroy conductors and components. It's this accidental interaction that might happen. So I think signs would be a great idea, actually. So to differentiate between those two types of systems, and often during firefighting procedures, there's a process after the fire has been extinguished too, that's called overhaul, where they will remove equipment, and they often use like a metal hook or something, drag stuff out of the way. They're looking for embers and wood and things that are remaining, burning and smoking and things like that. So during that overhaul procedure, stuff is actually getting moved around, and it would be nice to know, is that thing that you're moving around, is that a guard that you shouldn't move, right? Or wire management system that you shouldn't mess with? Or is it turned off due to some rapid shutdown device? So I think signs would be a good thing.
Agreed, Jason. And I think to your point, there's a lot of training required as well to make sure people know that. Yeah. Okay, there's one here. I think, Jacob, this might be a good one for you. Do the string isolation devices need to be UL listed with the racking system?
Okay, yeah, so it's important to distinguish string isolation devices from listed PV rapid shutdown equipment. So the listing for that rapid shutdown equipment is UL 1741. That PV rapid shutdown equipment handles what's outside of the array boundary. As far as UL 3741, that handles what's inside the array boundary. So it's necessary in cases where you have strings that are crossing between two distinct array boundaries. That area in the middle, that's where you need to have 1741 listed PV rapid shutdown equipment in place.
Okay, that's very helpful. Great. And then with SolarEdge, if there is an arc fault, does that shut down just the unit, or does that shut down the whole system? Clever, you want to take that one?
Would you mind repeating the question, Varsha?
Yeah,
sorry.
Sure. So it says with SolarEdge, if there is an arc fault, does that shut down just the unit, or does that shut down the whole system?
Good question. So yes, if currently the way that we have is that if there is if the unit detects an arc fault or ground fault, or even like I mentioned, like the beginning or a suspicion of an arc fault, the inverter only is shut down, not the whole system. So the whole inverter will be shut down, and the nice thing, right, is that with this optimization.
Clever, did we lose you?
Yeah, I can't hear him.
Clever, I think we lost you. We can't hear you anymore.
I can pick up.
Yeah. Let me, Clever, while we wait for you, I'm just gonna ask a couple of other questions here. Okay, so Jason, there is another question. I hear dangerous voltage being mentioned repeatedly. However, isn't a basic electrical principle that voltage alone does not present any danger to the human body? The individual would need to become part of the circuit in order to be in danger. I think you addressed this in the beginning, but would be nice to clarify.
That's right. Yeah, that's right. So yeah, voltage alone it isn't dangerous. It's the current that causes the. If you remember that table, it showed muscular contraction, defibrillation, which is like your heart not beating correctly. It's pretty scary, right? That's what happens with the current. So the standard is looking for a current path. So there has to be kind of 2 points of contact, if you will, right? So that's kind of the bird on the wire theory. If you just bird sitting on a wire is okay, but if they touch the pole or the ground or another wire, then they're gone. So yeah, so the model actually looks at during the firefighter interact. The model looks at the current through the body, and then the interaction looks at the firefighter. For example, we used hand to hip, right? So falling on the array with a sharp tool, right? So current's going through your hand, and then your hip is landing on a part of the racking system. So those are the 2 points. And so the voltage would drive that current through the body. So I put voltage up there on the slide just so people could visualize what voltage magnitudes are needed to drive those currents. Somebody asked me that once, what does it take to drive 100 milliamps through the firefighter resistance model? And so it kind of depends on the interaction, but let's pick an interaction that looks like it's, what do we put on there? 300 volts or so. Once you're at 300 volts, you're getting 100 milliamps in that hand-to-hip interaction. So.
And Jason, since we're on the topic of voltage, there's one more question here. Per UL 3741, what is the maximum voltage now? And what about if the firefighter is wearing gloves and insulating gear?
Oh, the maximum voltage allowed. So that's driven by NEC. So on the rooftop, it's 1,000 volts, right? And you do get to count when you do the resistance model. You do count the gloves and the boots and the body. So so again, I think back we have that chart up still at 1,000 volts. Even with this chart assumes all the PPE is worn. So this is falling on the array with the tool and belt with the PPE. So whatever resistance protection that clothing and those gloves and boots offer is included in the model. So you can see at the higher voltages, it's easy to drive current through those. The gloves aren't really electrically rated, which is what we heard from Tony Granato, who spoke on one of our other webinars. They're not rated for that use, but they do offer some resistance. So that resistance was actually tested during that research project that UL and Sandia did. They took different manufacturers' gloves and boots, etc., wet, dry, and looked at what the resistance values were because they don't come with like an electrical rating. So that is taken into consideration.
Okay, thank you, Jason. Let's see here. So Jacob, I think this might be a good one for you. Why is there extra cost for array inspection when not using DC optimization? For instance, are there any connector inspections involved? Or it could be for Jason as well. Whoever wants to take it, please do.
I can speak to it. There's more components of array that need to be inspected if you're not using DC optimization. So if you have a DC optimization solution, the components are listed. That is, their inspection was done beforehand, and you don't need to inspect the additional components, if it's the cable ties or how the hazards are being protected using mechanical means. If you are using that version of solution for 3741 compliance, then there's more components to that inspection, which is probably what's driving up the cost of the inspection itself.
Yeah.
Got it.
I think in some of the manuals we saw about 50 different components. Some of those are choices, but it was hard to determine which one was which. There's different types of wire trays, different wire management clips, different inverter models, different PV module models, different racking rails, clips. There's just a myriad of different things that it takes to maintain that robust mechanical system. So that would all need to be accounted for.
Yep. Farsha, you hear me? You forgot.
Yeah,
Okay,
clever.
good. Sorry about that.
Yeah.
So
No
one more thing that I wanted to say is that also because we have our Sense Connect with the new optimizers that detect the temperature level, increase on temperature level on the connectors between optimizers and the output. So that's another factor that without this optimization, someone will have to go with a thermal camera and actually point under the arrays, under the panels to detect any increase in temperature on the connector. So with this optimization, you don't need to perform that task.
Got it. And Clever, since you're speaking about Sense Connect, there's a question here about the optimizers on the website, which is S1200 and S1201. So the question is, S1201 seems to comply with UL 3741, while S1200 does not. When should designers choose one model over the other?
Okay, that's a good point. So S1201 is for rooftop applications, and therefore that's why it complies with the 3741 standard. And S1200 is meant for ground mount systems, which does not need to achieve the 3741 compliance. So that's rooftop 1201 and the 1200 ground mount.
Okay, very helpful. Clever, thank you. I know we're over time. I'll just go through a couple more questions and then we'll let you go. There is one question here, Jacob. SolarEdge allows us to connect maximum 30 optimizers in 2-to-1 per string. Even though there is a jumper between the arrays, it will never exceed the 30 volts in 30 seconds when the rapid shutdown is activated. So why do we need to install a special device when the string is outside of the array?
Yeah, it's a good question. So with a SolarEdge system, you wouldn't need any special device to control voltage that extends beyond the array boundary, any string extending beyond the array boundary. This is a requirement for non-DC optimized racking solutions. They have to remain NEC compliant, which means controlling the voltage outside of the array boundary And that's when the UL listed PV rapid shutdown equipment or module level MLPE becomes necessary. That's for voltage outside of the array boundary.
That's right. Thanks, Jacob. Yeah, that's the advantage of using our DC optimized solution versus something without DC optimization or MLPE. Let's see, just a couple more. With the need for automatic mid-circuit interrupters and a few manufacturers making these, will there be guidance on standardizing these non-module level devices, including any sort of communication standard, such as SunSpec? Jacob, this one is for you.
Sure. Yeah. So we touched on this a couple of times, but it could mean two different things. Sometimes mid-circuit interrupter refers to a hazard control strategy within the array, where array is being segmented down to typically that 165 volts or lower level. If you're referring to the rapid shutdown equipment, that already is listed to the standard 1741. The mid-circuit interrupters would be at standard 3741 for the entire array subsystem level. But when we're talking about the entire rapid shutdown system, that includes inverters, PVRSE, a 3741 solution, a racking solution, the coordinated operation of that is checked as part of your NEC inspection. So check with your racking manufacturers. Some solutions need many coordinated device from different manufacturers. SolarEdge solution, for example, is covered just by the optimizers and inverters alone. And so there was a mention of SunSpec. SunSpec is an optional communication standard for OEMs to comply with. So there's no requirement that, for a specific communication type.
Okay, makes sense. Thanks, Jacob. And Jason, maybe one last question that we'll take. Does SolarEdge have material available online that I could provide to the fire inspectors upon my post-install inspections of our compliance to UL 3741?
Yes, so that would be in the three-phase installation manual. It does cover the proper installation of our 2-to-1 optimizer, and we actually do call out the PV hazard control system. For us, it's pretty simple, but just to note for everybody, that is required by 3741. So there's a section called manuals and markings on the product, and it gives all the information that has to be put in the manual. So you have to list all of the critical components. In our case, it's two. It's the optimizer and the inverter. You have to use that combination, right? You can't go use some other combination. With other systems, it might be module type, racking type, inverter type, wire management, wire tray, etc. So the manual should have all of those bits and pieces, and they should have diagrams. They're required. That's part of the evaluation. When you go to the NERDL, you have to show them your manual. They'll double check to make sure all that information is in there. So that would be the guide. Some manufacturers might have a specific, inspection checklist. I would ask them for that.
Yeah, thank you, Jason. Yeah, and I think that's it. Many people just said it's an excellent webinar, and with the NEC to be adopted by most jurisdictions next year, this stuff will become very important. We do agree with that. And with that, let me just thank Jacob, Jason, and Clever here for joining me on this webinar today and sharing their UL 3741 expertise. We all learned a lot today, and I hope to see you all at the next webinar. And yeah, thank you so much for attending this, and thank you for your valuable time today. Have a great day, everyone.
Thanks,
Goodbye.
everyone.
Take care.
Thanks. Bye.